The other segment for chapter 11 that we need to talk about is about stress and strain. We've already talked a little bit about Hooke's law, the relationship between the force applied to a spring and the elongation, the resulting elongation of the spring as proportional to its spring constant or stiffness constant. And that's what I've tried to indicate here with the rest of this annotation. Think about the force that we apply as a stimulus, a cause, and the elongation as the response or the effect. If we talk about the ratio between, or the proportionality between the stimulus and the response, we're talking about the stiffness of that spring. If a given stimulus produces less response, that's because the spring is more resistant to stimulus. It's stiffer, it's more rigid, and so we say that it's stiffer. Yeah, it has a greater spring constant. Springs, though, aren't the only thing that we can do this with. We could talk about the force applied to a rubber band and the elongation response. Or we could think about, let's see, the sort of volumetric force applied to an air bubble underwater and how that bubble changes size. Or we could think about the sort of slicing effect of scissors or earthquake forces. And these are all applied to not necessarily springs, but solids of all types, rubber or, physical materials. So we'd like a sort of a general form to quantify, to sort of model stimulus response proportionality when we find it in materials of all kinds. Well, let's model it after this. Instead of stimulus, let's say stress. And instead of response, we will say strain. And the proportionality between the two, we're just going to call the modulus. Think about it as stiffness, but this is a particular word that has to do with the response of especially sort of bulk media, solids and liquids primarily. And it does change depending on what kind of stress we're subjecting it to. So really quick, I'll just go over the three kinds and the formulas we have for them after I define stress and strain, because these are new words and we need a way to define those words. Okay. So we need definitions for stress and strain. Stress, I'd like to define as the force applied divided by the area over which it is applied. So, for example, the rubber band I was just talking about, if we stretch some of it, we're applying a force to do that, and the area over which that stretching force is applied is the cross-sectional area of the rubber band. So we stretch, and that force is sort of distributed over the cross-sectional area of the rubber band. The ratio is the stress. The strain is the response, and it's the I'll use a different color. Strain is the fractional change in the relevant measurement of the object. So again, in the case of the rubber band, the rubber band stretches some length, some additional length. That change in the length compared to the original length that it had, that fractional change relative to the original length, that's strain. Okay, we are talking about, with the rubber band, a stretching kind of deformation, and I'd like to call that, really, we're subjecting the rubber band to tension. It's just, unlike a string, which does not stretch, the rubber band does. So here we're talking about tensile stress. And here, the relationship between stress and strain, the modulus with which we keep track of tensile response, is Young's modulus, and it's something we go look up in a table for the material in question. We can look it up for rubber or steel or copper or whatever substance you like. Since we're subjecting these materials to tension, we're talking about a change along the direction that the force acts. And the reason I'm using both hands to talk about tension is we're here in the equilibrium chapter. If we were we had an object, right? Some stretch of rubber, and we apply a force here on this side, well, the whole piece is just going to move because there's a net force on it, and the whole, it'll accelerate according to its mass. We need the net force on the object to be zero so that we can deform the object. If we're not talking about equilibrium, then there's no reason to deform the object. It's not going to respond that way. So we're talking about Young's modulus, the stress we're going to apply. So let's say we're talking about an object like this, and we're going to apply a force to stretch it on each end. The area of that face, that's the area that we're talking about when we apply that force. So we've got our force applied, divided by that cross-sectional area. The strain, we're talking about a length, a linear change in dimension, in shape. So we've got a delta L as compared to the original length, L0. And that's all proportional to Y, the Young's modulus. Okay, cool. One of our worksheets, Tuesday, practices using these equations. So don't worry if it feels a little bit odd for now. The worksheet is modeled after the examples in the book. So it's intended to be relatively straightforward. I gotta erase this so I can keep going. There's another kind of stress that we'd like to talk about. Instead of a length change, I'd like to talk about a volume change that results when we compress a thing from all sides. like a ping pong ball, I suppose. If we took it deep into the ocean, eventually it would crush under the combined water pressure. That volumetric change is what we're talking about here. For bulk or volumetric stress, the ratio of stress to strain is called the bulk modulus. Again, that's something we look up in a table. Stress, we're still talking about force applied relative to surface area. Strain, we've got a volumetric change, delta V compared to V0. This force divided by area on all the surfaces of an object, we could call that pressure. Like we were talking about water pressure crushing a thing. Bulk modulus V. And the last kind of stress we're talking about is, I'm out of space, so I gotta, let's see, erase this. What we're talking about is shear stress. And this one is, I gotta draw the diagram for you. Suppose we've got an object like that, some sort of rectangular prism, and we apply a force on the top face, parallel to the face. If that's all the story was, then the thing would move. So let's also apply a force on the bottom face so that these two forces are equal and opposite. And it's not tensile. We're not stretching the thing. We're trying to slide the top relative to the bottom. I'll give you an example. Got our textbook here, and I'm gonna pull to my right with my right hand and push to my left with my left hand and change the shape of the cross section from, rectilinear to slant. That's the kind of, it's like scissors, right? One piece of a scissors goes one way past the other, and we're trying to tear the object along that place where we're, with scissors anyway, by applying too much shear stress. And that, like, too much stress is what the last section of chapter 11 is about, is elasticity, plasticity, fracture. And it's largely qualitative. There's not too much to present, but I do recommend that you check that section out. So this is the last kind of stress we are talking about, and it is shear, not like fabric, not this way, not sheer fabric or sheer insanity, but sheer like shearing a sheep or the haircut I desperately need. So we're comparing the stress to the strain, and as you might guess, we're talking about a shear modulus S. And again, that's something we look up in a table. Okay, stress Here again, we're talking about a force applied divided by an area, but this time it's the area that is sort of parallel to the force that we're using, not the area perpendicular to, like when we were talking about tensile stress. The strain, though, how do we measure how do we measure the change from this orientation? Well, I can't even draw it, first of all. How do we measure the change from rectilinear to slant like this? That is a good question, because what are we, so stress over strain. Strain is supposed to be the fractional change divided by the original value. Just say initial value. But the initial value, it's not slanted at all to begin with. So what do we use? What's our reference, right? What's the original value that we compare to? So for stress, we have to, or for shear stress, we have to modify our definition of strain just a little bit. We create a lateral motion. I'm going to call it delta. The textbook calls it just X, I think, but I'm going to call it delta. And we're going to compare that to the original thickness of this material, sort of the distance between the faces on which the shearing force is applied. So that's this distance here. And I'll call that H. And that's equal to the shear stress. Oh, I'm sorry, shear modulus. So there we have it. I needed to present these, and then we'll work through worksheet 11.1 to practice applying them, and that'll be that. Thanks, everybody.